So we're going to start out today with our trig functions by looking at these things geometrically again. So we've drawn this picture a ton, but we're going to draw our reference triangle in the first quadrant. And what we're going to do is we're going to derive some of our Pythagorean identities or trigonometric identities that you might already know some of them or have used them before in Algebra 2, but we're going to see where they come from today. And then these 4 or 3 that we derive, these are definitely identities that you need to know, and you need to memorize those. So here's our reference triangle and our angle in our first quadrant. We've already labeled this would be, if this is our point and this is our terminal side, this would be my x value, my y value, and this is our hypotenuse of that triangle. And we know that the sine of theta is equal to y over r, and we know cosine of theta is x over r, and we know tangent of theta is y over x. Main reason we have some Pythagorean identities is to do some manipulations later when we do trigonometric proofs or proving those things, but also sometimes we can't draw things very geometrically. It's harder to actually represent these things, so we use the Pythagorean identities to help us out. So the way we're going to start is we are going to look at this triangle and figure out things that we know about it. I know it's a right triangle, so I know that I can use, since we're talking about Pythagorean identities, it's a safe bet to say that we're going to use the Pythagorean theorem. So I'm going to start with that. And then we're going to manipulate this to come up with some sort of substitutions to actually go through trig. So we know that these trig values are a ratio of different side lengths, and right now I just have the side length, so let's make it into a ratio. So let's manipulate it a little bit to make it into some fraction. I'm going to divide everything by r squared. I can do that because r is just a value, so I'm just dividing everything by 5 or 10 or whatever r is. And if I do that, I'm going to rearrange this. I'm going to make that x over r quantity squared, y over r quantity squared, and r squared divided by r squared is just 1. And now I can make some substitution with some trig values because I know that x over r is really cosine squared, and I know y over r is really sine squared, and those two values added together is 1. So that's our first trigonometric or Pythagorean identity, is sine squared plus cosine squared equals 1. And by the way, when I write it this way, sine squared, these mean the same thing. So sine of theta quantity squared is the same thing as sine squared of theta, but don't confuse that with sine of theta squared. Those aren't the same thing. So this is not equivalent, but these two are. So we're going to do the same thing. We're going to start out with our Pythagorean theorem. And we're going to instead of dividing by r squared on both sides, we are going to divide everything by x squared and see where that leads us. Because again, x is just some number. So if I divide everything by x squared, I'll get 1. And use the same trick. I'll have y over x quantity squared and r over x quantity squared. So y over x is y over x is tangent. So I have tangent squared. And r over x looks like cosine, but it's a reciprocal, so the reciprocal of cosine is going to be secant. So that's our second trig identity, is 1 plus tangent squared of theta equals secant squared. And last time we're going to do the same thing, except this time, you guessed it, we're going to, instead of dividing by x squared or r squared, we're going to see what happens if we divide by y squared. So I will get x over y squared plus 1 equals r over y quantity squared. X over y is like tangent, except it's a reciprocal, so that would be cotangent. And r over y is like sine, except it's a reciprocal, so that would be cosecant. So that's our third one, is cotangent squared plus 1 equals cosecant. Could have written it the other way, I probably should have, but that's okay. So these are our three trig identities, or Pythagorean identities. You need to know these by heart, so that way you can apply them. And we have two quotient identities. We're not going to derive these, but they're really easily derived. The first one is that tangent of theta can also be represented as sine of theta and cosine of theta over cosine of theta, and cotangent of theta, since it's just a reciprocal, is cosine of theta over sine of theta. So we are going to come up with these quotient identities in example 1. We're going to use this part here to come up with our sine and our cosine value given our tangent. And this is really similar to things that we've already done, except I don't think it's been phrased quite this way, where we're actually given like a trig function and then we're given a quadrant and we have to figure out what our other values are. So we're going to think about this one geometrically, and then the other ones that we do today, we're going to use our we're going to go away from our reference triangle and we're going to use our Pythagorean identities to get there. So we're trying to find the sine and cosine. If the tangent of theta is 4 over 3, this ratio, and theta is in quadrant 3. So when we draw in our triangle here, we're going to draw our reference triangle in quadrant 3. And this is really important. In quadrant 3, our x values and our y values are negative. So when we come up with our sine and our cosine, we have to make sure that those things are negative. This is the number one mistake that people do, is they forget what quadrant you're in, and then all of your answers will be missing a negative, and you'll lose big points for that. So if the tangent is 4 over 3, that's opposite over our adjacent, and again, these are in quadrant 3, so we'll make sure to put negatives on there. And this is a 3, 4, 5 triangle. Our R value is going to be positive no matter what. And here's our theta. So this one's nice and simple. Our sine is going to be negative 5 over 4, and our cosine is going to be negative 3 over 5 of theta. So if I wasn't doing that, and if we just decided that tangent was sine over cosine, how come we couldn't just say, all right, well, if tangent theta is 4 over 3, then sine must be 4 and cosine must be 3. Like, why isn't that also the case? And you might be thinking back to the lesson today, and you might be thinking, okay, well, I actually know that sine theta can't be 4 because that is out of the range. So that's maybe the one top reason, is that 4 and 3 are out of the range for sine and cosine, which we know from today is negative 1 to 1. They can only be between those values. So 4 and 3 definitely don't actually fall in that range. But the other main reason why we can't just do that, we can't just like pick and choose how we do that and kind of match those pieces, is because tangent, as we know, and sine and cosine, as we know, are ratio of side lengths. So tangent, sine, cosine are ratios of side lengths. And if we actually did plug in our values here, if we took the ratio of those two things, what would happen is that tangent would be a reduced version. So tangent gives a reduced or simplified ratio. So instead, we could write tangent, thinking of that problem, we could write it as a ratio of sine and cosine, which would be negative 4 over 5 and negative 3 over 5. And what that does is it simplifies down to 4 over 3. So these things are equivalent, but that doesn't mean that sine is 4 and cosine is 3. So you have to be a little bit careful when you're going through, because our tangent is always something that's simplified and reduced down. So our hypotenuses cancel out, in other words, to come up with our tangent. Okay, so again, what we're going to do in the back for these two examples is we are going to use our trigonometric identities rather than our geometric way to come up with our trig values. Now, I don't really care which one you do. For this one, if it were me doing this one, I would probably stick with the geometric way, because I think that for this one especially is a little bit easier. But for number 3, you can't really do a geometric way with this 0.7319. It's not a very good ratio to actually find. It's still possible, but it's something that is a little bit harder, and it's just easier to look at the formula for it. So again, we're going to use the Pythagorean identity. So I'm going to write them here: sine of theta plus cosine squared of theta equals 1. And we know 1 plus tangent squared of theta equals secant squared theta. And we also know 1 plus cotangent equals cosecant. So those are our main identities. For this one, we're given our angles alpha. It's telling us that our cosine is negative and our sine of alpha is positive. So cosine, which goes along with our x values, is negative. Sine goes along with our y values is positive. So that means that we're sitting in quadrant 2. And again, it's super important that we know this, because that will dictate our signs for our tangent as well. In quadrant 2, since x is negative and y is positive, that means that our tangent and our cotangent are going to be negative. So if you forget your negatives, again, you're going to lose major points, and this is like the number one area that people lose points in, is they don't remember what quadrant they're in, and then they don't actually include that. So if cosine is this, so we're trying to find all of our values, so I'm going to stick with the one that I know right now that deals with cosine. So I'm going to use sine squared and, I'll use alpha in this case. And cosine squared equals 1. And I'll make a substitution because I know cosine is negative root 3 over 4. When I don't know what sine is, and that equals 1. And so now it's just like an equation I can solve. So if I square that, I square top and bottom. So negative root 3 squared is positive 3. 4 squared is 16 equals 1. And then I'll move over, subtract 3/16 from both sides. So that'd be 16 over 16 minus 3 over 16, which is going to be 13 over 16. And then we take the square root. And I'm going to stress this, that we always include a plus or minus when we take the square root. But they tell us that the sign is positive, so we're going to use the positive version of this. But it's important that we just have a good habit of that. So we'll have positive root 13, and then the square root of 16 is going to be 4. So there's sine, and we might as well find cosecant now. So if I take the reciprocal, it's going to be 4 over root 13, and I'll rationalize, so you get 4 root 13 over 13. So those are our two. And we can do the same thing for cosine to find secant. So the secant of alpha is going to be the reciprocal of that, so negative 4 over root 3. And again, if I rationalize, I'll get secant is equal to 4 root 3 over 3. Okay, good so far. So now that we have, here's cosine. Now that we have these four, we can find our tangent and our cotangent. We could use this formula if we wanted, since now we know secant, and plug it in and then solve for tangent. But we can also use our quotient identities and just do sine over cosine. So if I'm trying to find tangent of alpha, I can do sine of alpha over cosine of alpha. and I know that my sine value is root 13 over 4, and I know my cosine value is negative root 3 over 4. So if I multiply by the reciprocal here, so if I take this and then multiply that on top, I'd get negative 4 over root 3. My 4's would cancel out, and then I'm left with negative root 13 over root 3. And I got to rationalize that again, so I'm going to multiply by root 3 over root 3. When I do that, when I multiply these radicals, that just means that I'm going to keep the radical and then multiply the values that I have. So 13 times 3 is 39 over 3. So there's tangent. And I could flip that, but I'm actually just going to find cotangent by looking at the reciprocal of cosine and sine. So or I could just like flip it here. Either way, if you did do the sine and cosine, you'd have cosine on top and sine on bottom. And again, the 4's would end up just canceling out. But we can flip this one right here, so it'd be negative root 3 over 13. And then we got to rationalize. So we'll get something really similar as our tangent. We'll get negative root 39 over 13 for that one. So again, we did all that, found all of those different ratios by using identities, and instead of using like a geometric way. But either way, you could do it either. I want you to try for like the practice tomorrow to use the identities, because the more you're familiar with them, the easier that'll get to remember them. But again, like in the future, unless it specifically says, which I don't think that, I think you have either method, you can just use like a geometric way. But this one is something that is harder to use a geometric way for. So we're given tangent is some decimal approximation, and we're trying to find the cosine of b. So this time we're not actually looking for all of the trig values, we're only looking for one. And we know that we have certain trig value or trig identities that go along with tangent. So we're going to think about this one here, the second one, the 1 plus tangent squared of theta equals secant squared. And again, I'm picking that one specifically because we're given tangent and we're actually looking for cosine, which is just like is the reciprocal of secant. So this kind of falls nicely into place. So if I do replace that, so I'll replace tangent with the 0.7319 squared equals secant squared. And then I'll find what that is in my calculator, 1 plus 0.7319 squared. So I get 1.53567, I'll round, equals secant squared of theta. And to solve, we'll take the square root plus or minus square root. So I'll take the square root of that and I'll get 1.23922. And again, when we're taking the plus or minus square root, we have to make sure that we know what quadrant we're in. This it's telling us that tangent is positive. So tangent's positive, cosine is positive, which means that we are in quadrant 1. We don't even actually necessarily need to know the quadrant for this one because we're looking for our secant value. And if we know that our cosine is positive, that means that secant's positive as well. So we're going to take the positive version of that. And to solve this, I know that secant is 1 over cosine. So what I could do is I could put this over 1, cross multiply, and solve for cosine. But if I have a reciprocal on this side, I can just take the reciprocal on that side too to solve that. So 1 over the 1.23922 is going to be cosine. So 1 divided by our answer will give us that our cosine is 0.807. And that's all we're looking for in that one. So this one's a lot easier to do, I think, with the Pythagorean identities rather than doing a geometric, because we don't really have a ratio here to apply.